So today we're going to look at Chapter 8, Chemical Equations. In this chapter, we're going to use these terms quite often, so I want you to understand what they mean. When there is anything in front of the arrow sign, we call that a reactant. The arrow is called the yield sign, and then anything after the arrow is called a product. Okay? So I'm going to be using those terms throughout this chapter. Now we're also going to focus on how to balance reactions. To balance reactions, we want to balance in between the front of the arrow and the back of the arrow. So we're basically balancing it right down the middle, and we want to balance the atoms, not the compounds. So when I do this, I like to make a chart to help me. So I look at all the elements that exist on the left side. In this case, it's aluminum, iron, and oxygen. Now, as usual, it is going to be the exact same elements on the other side. I like to put them in the same order to help me understand, what I'm looking at and make sure I'm looking at the same element. So I say, how many are there? Currently, aluminum only has one. You'd find a number kind of written below here if there were more. So nothing assumes a 1. Iron, there is 2. And oxygen, there is 3. Okay. Aluminum on the right side has 2. Iron has 1. And oxygen has 3. Now, that is just the start of figuring out how to balance. Now, the next thing you want to do is now get these elements to have the same numbers on each side. I'm going to first focus on aluminum. Aluminum has 1 on this side and 2 on this side. I can only increase the number, so I cannot get a 2 to become a 1, but I can add a 2 in front to then have 2 aluminum. Now, we call this a coefficient. We're going to be referring to that a lot. So it is the number in front of it. It is never the number that is down below. It is the number in front. It's called a coefficient. So now aluminum is done. Iron has 2 on this side and 1 on this side. I'm going to add a 2 to then make iron have 2. So we are good on the irons. And then oxygen in this case has 3 on this side and 3 on the other side. So they are actually both good. Now you can leave this as is, or you can put 1s here. It's whatever you're comfortable with. So again, we have 2, 1, 2, 1. So you can put the 1s, you don't have to. Now, if possible, when you are balancing, if you notice that your numbers can be simplified into a 2, 1, 2, 1, that is what you want to do. Okay, it's easier when we do the math portion of this. It'll save you a lot of time to have lower coefficients. So just keep an eye out for that. Now, other things we're going to be focusing on in this chapter are phases of different reactants and products. S means solid. AQ means it is an ionic compound. Remember, that's a metal and a nonmetal. Dissolved in water. Okay, that's what AQ means. L is liquid, and we usually do cursive L, so please try to do that because a lowercase l just looks like a 1, so it gets confusing. G for gas, and then heat is given by this triangle, which we have referred to as delta. Oftentimes we do it right above the arrow sign to indicate that heat has been added to the reaction. Now, another term that we're going to look at that we have focused on in the past is the law of conservation of mass. This means there is no change in the total mass in a chemical reaction. So if I have methane, CH4, and O2, and I have 2 grams amount of them, if we add those up in our reactant side, we'll have 80 grams. If I add it up on the product side, I will also have 80 grams. And that satisfies the law of conservation of mass. 5 types of reactions we're going to focus on. Synthesis, which is also called combination. Sometimes you'll see it as metathesis, depending on what you're reading or where you're seeing it. We have decomp, single displacement or replacement, either way, double displacement or double replacement, and the last one is combustion. And combustion is when an organic, which we'll talk about what that means, burns with oxygen. Okay? So first thing we're going to focus on is a synthesis reaction, and you will have to know how to predict the products for these. So it is characterized by having an element plus another element, and we put them together to create a compound product. Let's do an example. We have magnesium plus we have oxygen. Now I'm going to put a 2 here, but we will talk about very soon why that is a 2 and why the magnesium is not. So just stick with me here. And then when we put together magnesium oxide, we need to know the charges. So this takes into account the charges from the periodic table. Mg is in group 2, so it gets a +2. Oxide is in -2. You crisscross those, they cancel out, it becomes MgO. Now if we are balancing, which we want to get used to balancing, we have 1 Mg, 1 O on this side, we have 2 on this side, so we're going to go ahead and put some 2's to counteract that. Now if you want to do that slower, I completely understand. You can always refer back to writing a chart with the elements below it if you are more of a visual person, seeing how many you have, and then canceling. But if you can do it in your head, or on the paper, that's also fine. Many options. All right, now this number right here indicates the charge. That is not a coefficient in front. So this is basically the same as saying chromium +3. So we have chromium, we have oxygen, and then when we put them together, we have to take into account the charges. So Cr, as shown, is a +3. Oxygen is in group 16. It is a -2. We crisscross and we come down, and our products are Cr2O3. Then you, of course, you don't want to have that written there as well. Okay, then we're going to go ahead and balance. So I have 2 chromiums on this side. I can put 2 over here. We do not take into account this when we balance. We only look at the number of elements. So now 2's are good. Oxygen has 2 on this side. It has 3 on this side. The only way I can get a 2 to become a 3 or a 3 to become a 2 is to make it 6. So I'm going to multiply this by 2, this by 3, but then this ends up being a 4. Now, if you're struggling at all with balancing, or if you haven't done balancing, please refer to a YouTube video that I will link in this same week's folder to do some practice balancing. All right, now we have sodium and we have chlorine, and I told you I will remind you very soon why this one has a 2 and this one does not. So when you put them together, Na is always a +1, Cl is always a -1. When you make them a compound, they become NaCl. Okay, so if we balance that, we have 2 chlorines on the left side, so we're going to put 2 here. That also affects the Na, so we're going to put a 2 there. I like to put the 1, but you can also skip the 1. All right, so some tips when you predict products. When you have an element by itself, this is the big thing here, and it is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, or fluorine, they are more stable in a form of 2. We call this diatomic. Okay, these are diatomic elements. So if it is any of these and it is by itself, not in a compound, it has to be by itself, then you have to put the 2 here for all of these. Now, my little memory trick is called Brinkelhoff. It's a funky saying, but if you say that, Brinclhoff, Brinkelhoff, that helps you remember what elements need to be in a form of 2. Also, we're going to start talking about phases. So I just want to indicate all of these are gases at room temperature. The only one that differs here is bromine, which is a liquid. Okay, so please make sure you recognize that. Now, every other element that is not part of Brinkelhoff is by itself, and it does not have, nothing is written down below. It is just copper or silver or sodium or nickel or anything other than the ones up above. So if it's by itself, you don't have to do anything but write the element. Now, these are all solids at room temperature. All right, so let's take some of those rules and start doing another type of reaction, which is called decomposition. So what we have is one reactant, and it is breaking apart into its components. So for example, if we have copper oxide, if you are still struggling with this, make sure you go ahead and write your elements, and then you crisscross and come down. And we break that apart into copper. Now, copper is not part of Brinkelhoff, so it is just Cu. And then oxygen, or molecular oxygen, is O, but it's part of that Brinkelhoff, so you put a 2. We're also going to start going ahead and putting the phases. Copper, I told you, is a solid, and oxygen is a gas at room temperature. And then this would have been told you to be a solid. So let's go ahead and do PbO2. So again, all we have to do is break it apart. Pb, it's a solid. We'll balance these, of course. And then O, and O is part of Brinkelhoff, so it gets a 2, and that is a gas. Okay? So do not take into account the numbers that you find in the initial reactions. You want to just decide when you create your products, is it part of Brinkelhoff or is it not? Those are the only two questions you ask yourself. So this one is actually all balanced for us. This one requires a 2 here. Actually, this will be a 2 here, and this would actually be a 4. Oh, sorry, there was some weird formatting on here. So just to reiterate what that would look like, it'd be 2Cu2O yields 4Cu solid plus O2. Okay? Sorry about that. All right, and the last one we're looking at here is KCl. So when we split that up, it would be K, not part of Brinkelhoff. Cl, it is part of Brinkelhoff. That is A2. And that has a gas, and this is a solid. Okay? And to balance it, we'll put a 2 here and a 2 here. So those are currently the only two products you need to know how to predict. Now, I'm going to be providing you with this chart. This is solubility rules. It basically means what would dissolve if it were in something else, okay, in water specifically. So you are going to have this. You just have to know how to use it. I do want to indicate two things. If it's an S, I know this is kind of counterproductive, but this means that it is a solid, okay, in water. Where AQ means it is aqueous. Or basically it breaks apart into a solution. Okay, so solid means it doesn't dissolve. Another word for S would be insoluble, where soluble would be more applicable to the AQ. Okay? So you're going to want to see what your compound matches with. If it has any of these, then you would read the rules or the exceptions. We'll do some examples of those in class. But you will always have that available to you. All right, now single displacement or single replacement, you will not have to predict these products at this time, okay? But it is character. You will have to identify that it is what this is. It is a single element, usually a metal, with a salt. I want to remind you, a salt just means an ionic compound. That's all it's saying. Fancy word for ionic compound, which is a metal and a non-metal. And then what is happening is the metal is pushing out the other metal, which in this case is the B. B gets pushed out and A replaces it with C. So it's basically like switching partners, okay? So A was by itself, B was with C, B is now by itself, and A and C have now joined together. So let's see that down below in this example. We have a metal, we have a compound, or a salt, or an ionic compound, whatever you want to call it. The iron pushes out the copper, and you can see copper hanging out by itself, and now we have iron sulfate. Now what you will need to do is I want you to use your solubility rules and indicate what those are, okay? Either AQ or S. And then I want you to, of course, go ahead and balance. So I'm going to go ahead and work on that as well. You're welcome to pause here and do that and check your answer. So iron sulfate would be this rule. They are soluble. Okay. So they are soluble. That is AQ. And anything I told you a metal by itself is solid. Then we have copper nitrate. Anything nitrate is soluble. There are no exceptions, so that is AQ. Remember, soluble means AQ. Please excuse this. It should have been some subscripts there, and we know this to be solid. All right, I am going to now balance. So I see that I have one F over on this side. There's two F's over here. I'll put a 2 here. I have one SO4. So I like to look at this as a whole object when balancing. So one SO4 on that side, one on the other. So it's nice. It saves you a lot of time when you balance. Just like I like to look at this NO3 and this NO3. There's two sets of NO3, so there's 2 over here. I have one AG now on that side, so I want to balance that out. I have one copper, so I'm just going to fill those in with 1s. Again, you could leave those blank. All right, another type of single displacement reaction, you're not going to have to classify these other than single displacement. You will not have to say if it's a gas or a salt or a metal or anything like that at this point. Just recognizing you having one element, a compound, creating a new compound with a new element. So this zinc pushed out the H. The H is now by itself. It is in a form of 2 because it is part of Brinkelhoff. And then we have ZnCl2. We can go ahead and balance this. And we can also go ahead and write the phases. So go ahead and do that for me. This is a gas. I'm going to go back to the solubility rules for the ZnCl2. So I see Cl, not an exception, so it is AQ. And then if I balance it, I have 2 Cls, 2 and 2 there. Okay, so pretty easy balancing. Again, please refer to the balancing video if you are having any difficulties with that. All right, another type of reaction I want to introduce you to is double displacement. Double displacement is very similar to single replacement, except 2 things are switching partners. So A was initially with B. A has then switched and is now with D. So basically, I like to do the outers join together and the inners join together in the products. Okay? So when we're dealing with this, to recognize that, you want to make sure that something, instead of it being with the original pairing, it was with the other one. So BA joins NO3, and then AG joins the Cl for the other product. So go ahead and check your solubility rules for this. I know this one is AQ because it has a nitrate, and I need to go back to the Cls. So this is an exception, meaning it is going to be a solid. Now I wanted to do this one because when you have an aqueous as one of the products and an S as the other, this is what we call a precipitate. Okay, and you will have to recognize this. This is the precipitate. That is a solid product. Okay, but the other thing has to be aqueous. So if you had a reaction and one of them was a solid, is a product, it has to be a product. I would ask you, or I could ask you in a question to say which one is the precipitate. You would tell me it was the AgCl because that is the solid. Now I'm going to quickly balance this. Where's the okay. So 2 NO3s, 2 NO3s. Okay. All right. All right, moving on, practice balancing double displacement. Now, I really think it would be easier for you to see these NO3s as a whole set instead of just an individual N. So on the right side, I have 1 set of NO3. On the left side, I have 2 sets. So if I put a 2 in front of this, I now have, remember that goes to the K and that goes to the whole NO3. So now I have 2 Ks. I'm going to put a K over here. So I have 2 Ks and I also have 2 Is, which then counteracts this. Now, I wanted to show you again, if you're having trouble or you're just learning this, I suggest writing all the elements out. PB, NO3, K, I, PB, NO3, K, and I. Writing how many elements there are, of course, before you put all the numbers, and then working your way through each one. Okay, as you get better at this, you don't need to. I don't need to see that work on a test. It's just very helpful. So I see 1 Ag, I see 3 over here. I'm going to put a 3. Remember that 3 then goes to the NO3. Put a 3 for the NO3. 3 Ks. 1 set of PO4, 1 set of PO4. All right, in the last set, we have NH4. Now, again, these are hard when there's a lot of stuff going on. So we have this set. We have NH4. We have NH4. 2 HGs, 2 CLs. All right, I think we're good there. Okay. If you want some more practice doing the solubility, you could do the solubility for any of these. If you have any questions, you're welcome to email me and check. All right, another type of reaction, which we're not going to focus a ton on, but we will a little bit later in the year, is called titration or acid-base reactions. We know it's an acid. It has an AQ. It has an H in the front. And then we are going to learn eventually a base usually has an OH at the end. So this really is just another way of saying it is a double displacement reaction. The H joins with the OH. The Ba joins with the Cl. And we have our two products. Okay. You can go ahead and balance these like normal. Really, nothing is different with this. So I have one H, I have one H, I have one Cl, two Cls. I have two sets of OHs, one Ba, one Ba. Okay? Now, the one exception here is anytime you see HOH, which is actually also known as H2O, you have to know that that is a liquid. Okay, unless you're told otherwise. So I like to write HOH. It's easier to see the OH portion here so that you can compare it with this one. But if you prefer to write H2O, that's also up to you. Now, the last one you're going to have to know how to recognize in terms of balancing is combustion. Combustions are very simple. What it is an organic. What is an organic? An organic contains C's and H's. I'm just going to put X and Y because the numbers could be any sort of situation. Or a C, H, and an O. I'm going to put an X, Y, and a Z here. It could be either of these. And you're also always going to see an O2. And your products are always the same. Products are always CO2 and H2O. And you can write H2O and CO2, it doesn't matter. Now, you are going to have to recognize, hey, this is an organic. It has a CH or a CH and O. You can see that here, CH and O2. And you're automatically going to say CO2 plus H2O. Okay? Simplest ones. You just have to recognize them. Now, another thing you're going to have to do is balance them, which gets a little confusing. So 1 carbon on this side, 1 on this side, 4 on this side, 4 on this side. Then you have 2 oxygen. Now you have to add up the oxygens here. So there's 2 on this side and there are 4 on this side, which gets me a total of 6, which gives me then a total of 3 times 2 to get 6 as well. Okay. So another example of balancing, we have another set of combustion reactions, C and an H and an O2. Our reaction products are CO2 plus H2O, or again, you can write H2O and CO2. That's also perfectly fine. To balance this, same thing. We have 4 here. I'm going to put a 4. Remember that 4 goes to both the C and the O. We have 10 hydrogens, so I'm going to go ahead and put a 5 there. Now, this is where it gets a little funky. So I have at this point, how many? I have 8 oxygens here, and I also have 5 oxygens here. So if I add those up, obviously I get an odd number. When you add them up and got an odd number, 2 things you can do. You can use a fraction as your coefficient here. If you want to do that, you can do that on your own. I suggest when you have an odd number here, if you end up doubling these, just whatever the number is, double it. Everything will then work out better. So let's go ahead and start fresh again with our new numbers. So I have 8 carbons. So I'm going to put a 2 here. And I also have 20 hydrogens, which works well for both of those. Now, how many total oxygens do I have? 8 times 2 is 16. 10 times 2 is 10. I now have, 26 total oxygen. So since there's a 2 here, you have to cut that in half, and then I have 13. So my coefficients are 2, 13, 8, and 10. So when you get an odd number of oxygen, when you're balancing a combustion reaction, double your current coefficients. So read over this to make sure you know what you're going to have to know. You will have to understand how to predict products of 3 things: synthesis, decomp, and combustion. You have to classify as synthesis, decomp, single, double, or combustion, which you're going to do in your homework and on the book problems. And you also have to be able to use the solubility rules to predict solid, liquid, gas, or aqueous.